Hello students, for these slides you can just read this is about the course objectives. So in order not to uh, take time on the explanations and discussions on this, you just read this portion, although I uh, animate this, but you can read this. So these are the chapter or course objectives for supposedly structural theory 1 only. So I'll begin with this introductory discussion. So for the preceding slides, you can pause anytime you want if that was fast. So you can read and of course think also. So this is for historical background, so you can also read this by your own. And these are the topics: role of structural analysis in structural engineering projects. So I think I begin with the discussion with 1.2 and up to 1.4. So we define structural analysis as the prediction of the performance of a given structure under prescribed loads and or other external effects such as support movements and temperature changes. Now, these prescribed loads shall be estimated based on the table which will be provided based on the information of the materials density and other information based on experience. And of course, if the structure is subjected to external loadings caused by earthquake, wind, and other impacts due to movements of vehicles and so on and so forth. Or it depends on the type of structure where it is built for the public. The common performance characteristics of interest in the design of structures. These are the stresses or stress resultants, deflections, and support reactions. So these are the reports, performance characteristics or responses that must be accounted using statics and your knowledge background in statics and of the material characteristics, material strengths, no? Especially in the mechanics of materials also. So that's why in the mechanics of materials you should have experience on deflection problems so that you will be prepared to analyze indeterminate structures, not just determinate structures. For those who haven't experienced deflection uh, topics, I have deflection topics in the mechanics of materials. So if you haven't subscribed, please subscribe to my YouTube channel so that you will be updated of the lecture videos and sample problem videos that I will be uploading in YouTube. So first read the preliminary discussions on deflections, then you also study the sample problem videos, especially on double integration method. So as of the moment, you're just familiar with the double integration method of computing deflections. So these are about chapter objectives. You can go over this by your own. This is about the history of structural analysis. So I'll begin with the discussion here, the role of structural engineering in structural engineering projects. So structural engineering is the science and art of planning, designing, and constructing safe and economical structures that will serve their intended purposes. So the it involves planning, while in the planning, it's part of the type of material that will be used to resist loads. It may be dead loads or live loads, but to give you an idea, if the structure is exposed to wind, especially in coastal portion, and it is made of steel, then the structure made of steel will be subjected to wind loads. So the prevailing or the controlling load would be wind load for light structures such as steel. So if it is made of reinforced concrete, it is heavier, then it will be subjected to lateral earthquake loads. So that's the distinction. If the structure is light made of steel, then wind load controls as the lateral load. And if the structure is made of concrete, reinforced concrete, it is heavier, so it is the earthquake load that will govern in the lateral loads. So just to give you the idea. And in planning, of course, you have to select which one is effective to avoid maybe corrosion, maintenance that will cause economical impact to the structure. So while planning, the structure should be as much as possible economical. At the same time, of course, do not compromise its safety. And it will serve their intended purposes. For example, the lifespan of the structure should last about, let us say, 40 years before they will be dismantled and replaced with another new one. So that's just an example to give you an idea. So next we have pieces of typical structural engineering project. Although this is supposedly in the design or actual implementation of the project, where you have a team of builders to prepare the erection of the structure. So we have the planning phase. So we have the different people, professionals in this part to decide the type of material, the location, and the shape of the structure to be built. Then preliminary structural design. So that's not part of structural engineering, structural theory here. Then we have the estimation of load. So this is now part of structural theory, and of course in design phase. Then we have the structural analysis. So you're going to have approximate preliminary analysis first. So this is the part of structural theory, our subject matter. Then after that, we have to evaluate the safety and serviceability requirements satisfied. So when you say safety, are the stresses, maximum stresses for all parts of the structure less than the specified limits for safety purposes. Serviceability means the deflections are controlled like that. So will it cause damage? So if it will cause damage to the structure or part of the structure, then it should be redesigned. So after evaluating safety and serviceability, if the answer is no, then you have to proceed with back to estimation of loads. So maybe the estimation of loads, you made a little mistake here. You have to increase a little. So use the maximum density, for instance, then perform structural analysis again until such time that this base of safety and serviceability has been satisfied. So if it is yes, then proceed with the construction phase. So that's it. So our part here would be for this portion only. And of course, this is part of design. You will know that in design, you will have to evaluate the safety and serviceability requirements. So that's why I want you to be honest. You have to prepare yourselves because this subject is supposedly the most challenging subject of all subjects in civil engineering. Although it is a continuation of statics, but I'll tell you, this is the most challenging subjects in civil engineering. But if you are honest enough and you really want to learn, you want to enhance your skills in statics, then do it, because although design is simpler, you just generate the moments and bending moments, of course, maximum bending moments, so that you can evaluate the stresses afterwards. So I want you to train yourselves, and while training, be honest as much as possible. You can study independently, or you can consult your classmates who are good. But during quizzes, please try to be honest. It is in preparation for design. Anyway, you will suffer if you are not honest. In the planning phase, you need experience of people who are already structural engineers. This is very crucial, especially in the selection of materials and the type of construction procedures that must be applied in a certain structural project. So aside from safety, then preliminary structural design, this consists of selection of section sizes by approximate method and experience. So that's why you have to be part of the size. You should have experience from past projects so that you can select sections, you can assume, so that you can approximate the loads, dead loads especially, and live loads. Estimation of loads. Structural analysis, determination of stresses, reactions, deflections. So as I mentioned earlier, so this is after your background in statics and mechanics of materials. Then construction phase, preparation of drawings and layout. So that's part of the those who are involved in the construction phase. Drawings so that during construction you'll have a guide instructing the laborers, skilled laborers for erection of this project. Next, we have classification of structures. The most important decision made by a structural engineer is implementing an engineering project. In implementing an engineering project is the selection of the type of structures to be used for supporting or transmitting loads. So there are two or three. It may be purely steel or concrete. So if the structure is made of concrete, as much as possible, it should be placed if in coastal areas, for instance, I would suggest that the structure should be made of reinforced concrete because it is exposed to wind, and wind cannot affect so much to reinforced concrete structures because they are heavy. So it is earthquake that controls. So for coastal areas where structures are exposed to wind, I suggest that this should be made of reinforced concrete. And for areas where wind is not a problem, then you can have steel. As long as you have to maintain to prevent damage such as corrosion for steel, or if they are exposed to chemicals, so it should be protected so that the serviceability of the structure can be extended. So the type of classification structures would be tension structures such as cables, tension rods, and so on and so forth. Suspension bridges, etc. as shown in the figure. So we have here a cable subjected to concentrated loads. So we will also study this, although you have background of this supposedly in statics. Then the analysis involved. Then we have parabolic cables, suspension bridges. We have compression structures such as columns. This one, the opposite of concavity for cables. This is subjected to compression. This bridge here. We have here a beam column member. This one, part of a frame. Then we have columns and arches. We call this an arch. So beam column members, this one, subjected to lateral loads also. We have trusses. We have a bridge truss here. We also have a roof truss. Then shear structures. This is a building. So this is subjected to wind or earthquake. That's why this part of the wall is solid to resist shear. It may be also subjected to wind depending on the structure. And whichever has great effect, wind or earthquake. So if the earthquake lateral load causes greater value, then that controls. If wind controls, then that should also be the load of the wind that must control in the design of this structure here. Then bending structures such as beam and girders. So these are beams attached to girders. So girders are beams also that are greater in size than the floor beams. And surface structures. We will have, you cannot experience this because this requires great analysis. So this may be in post civil engineering courses. If you want to pursue doctoral degree, then you will definitely encounter surface structures. You will deal with the analysis of surface structures, such as this dome here, the roof made of concrete, which is very thin. So that's a surface part of called surface structure. An analytical model. An analytical model is a simplified representation or an idealization of a real structure for the purpose of analysis. The objective is to simplify the analysis of complicated structures. So that's the role of structural engineer. The loading is very complicated that sometimes they need to use numerical methods in order to derive the loading. So, but the structural engineer prefers to make it uniform so that the analysis would be simpler. So that's the role. Why make the loading difficult if the structural engineer uh, tries to simplify it by making it uniform? Then we have the case of uh, comparison. If the structure or part of the structure should be analyzed as purely plane or space structure. So for instance, we have here a footbridge, or maybe this is also allowed where motorcycles can pass over this bridge. Then for this case, of course, we can analyze this as a plane structure, and we have tributary areas. This one is a roof truss, so we can consider this as a plane truss. And these are the loads normal to the slope part of the top chords. These are wind loads definitely because they are perpendicular to the joints. Remember that for a truss, the loads should be transmitted to the joints, not on the member. So this is a plane truss. This is the real structure, and this is the idealization, the analytical model. Then we have here the beam column, this portion here. Then in the analytical model, it is drawn with lines and represented by these members and this girder here. And this is the load, which is uniform. It may be varying, but as I said, the structural engineer made it simpler by making it uniform, as shown in the figure. Then line diagrams. So these are the diagrams already. So we also have here a space truss, because we have here a space structure also. So this is analyzed as a space structure. Connections, whether the connection should be considered a pin or roller, where there is one reaction. So we have here typical pin supported construction. So these are considered pins that can resist horizontal and vertical movements. And this one is because the bolts are massive plus the weld, then this is considered as a fixed supported connection. Fixed supported connection. So you know already the fixed support from your experience with statics and mechanics of materials, as well as this pin support here, which is the same as this. Then supports, it may be a ruler, or you have another column as supports, which is considered fixed. Then loads and structures, we have dead loads. Dead loads are those that are permanently attached, fixed in position, such as the weight of the structure itself, like beams and so on and so forth. Then we also discussed live loads, the impact, wind loads, snow loads. So for wind loads, let's make it simplified. The discussion here in the NECP is very long and very complicated. The pressure diagram is logarithmic, so I will just leave that to you in your design part. It may be discussed, but in this subject, let's make everything simple by introduction of wind pressure coefficient that makes the loading uniform. As I said, let's make it simple because the result will be very close to that simple situations. Then snow loads, there is no snow in the Philippines, although part of the Philippines experienced uh, falling of ice even in Davao City, but there's no snow, of course. So I just discussed this very briefly. You will be introduced with the formulas, but we shall have, we will not concentrate on that. Then earthquake loads. So this will be discussed in your earthquake engineering subjects, but I will introduce this very briefly also. Hydrostatic and soil pressure. This will be in hydraulics partly, and of course in your geotechnical engineering. So I'll discuss this very briefly also as an introduction. Thermal and other effects such as uh, exposure to great temperature changes, which is not the case in the Philippines, only in polar regions, and other effects such as fabrication error and aside from thermal fabrication error, support movements and so on. Load combinations, this will be in design, but I'll introduce this. I'll give you the 2010 load combinations very briefly, and you can go over with them. Do not just familiar the first one, and for the rest, you are allowed to have an index card for that. So the objective of a structural engineer is to design a structure that will be able to withstand all the loads to which it is subjected while serving its intended purpose throughout its intended lifespan, as mentioned earlier. He or she must take into account all the loads that must realistically be expected to act on the structure during its planned lifespan. So of course, the problems I will create will be sometimes realistic, but when you say realistic, it should be based on the purpose of designing the structure. So based on experience also, and based on these topics that the structure must be subjected to. And we have chapter objectives again, so you just go over with that. So dead loads, as mentioned, are loads that are permanently attached to the structure, fixed in position such as the weight of the structural member itself. So these are gravity loads, and those that are permanently attached such as mechanical devices, fans, uh, ducts for air cons, and so on and so forth. But uh, the most important part of the dead load would be the structural member itself, such as the beam, columns, girders, and so on and so forth. So we have here the minimum densities for design loads from materials. This table is taken from the book by Hibbeler, your textbook. So you can have this in your estimation of the loads, dead loads. You can use this density in SI units. So they consist of the weights of the various structures structural members and the weights of any objects that are permanently attached to the structure. So this one is presented in my YouTube, and you can have this in Dagler also. So another table for minimum design dead loads. So you have here the walls, frame, partition walls, floor fill, ceilings, and so on and so forth. So you can go over with this. And I also have this example too, which I presented. The solution is presented in YouTube. And this one also. Also presented. Then let's proceed to live loads. Live loads are loads of varying magnitudes and or positions caused by use of the structure. Live loads can vary both in magnitude and location. So they are caused by weights of objects temporarily placed on a structure, moving vehicles, equipment, and so on and so forth, or natural forces such as wind, or there may be earthquakes that will come, or we have exposure to temperature changes. Live loads for buildings. So live loads for buildings are usually specified as uniformly distributed load, as mentioned earlier. People, transient people such as us, we are considered live loads. Although our weights are not uniform, but let's the structural engineer, for the purpose of simpler analysis, made them surface loads in kilopascals that are uniform. And this is found in building codes in ECP for the type of functions that part of the structure may be functioning or performing. Other loading guides are provided by the following respective agencies responsible for the different fields of engineering. So in our case, we have the NECP as our guide, and for other agencies such as DPWH in the Philippines. So in the US, we have ASTO for bridge design specification, Highway Transportation Officials. Area for steel railway bridges, American Railway Engineering Association of Railway Engineering, or maybe American. So you just go over with this acronym, and I want you to answer this because this is also important. The important thing to remember about specifications, therefore, is that they are not written for the purpose of restricting engineers, but for the purpose of protecting the public. So that's the thing that are written in specifications so that the public will be protected for possible uh, emergencies, disasters that will happen to the structure. So it is the safety of the lives of the occupants of that structure. That's the main purpose of about specifications. They are not intended for restricting, making the structural engineer go over with the problems by stressing them, but for protecting the public. That's the most important about specifications. So we have here the table for minimum live loads, as I mentioned, in kilopascals for occupancy or use of the building or other structures. So we have assembly areas, fixed seats, office buildings, in the lobbies. We have here the live load in pounds per square foot and the corresponding SI load in kilonewton per square meter per floor area. We have storage, residential, and schools. So let's go over with this. Live loads are tolerated to be reduced according to the formulas given below because it is unlikely that the prescribed live load will occur simultaneously throughout the entire structure at any one time. So for instance, it is impossible that a building will be occupied fully during any one time. So there should be a space where there are no people or there are no loads, live loads, occupants for the entire floor of a building. So that's the reason we can reduce the live loads according to these formulas here. So we have here the reduced live load L. This is the designed live load, and this factor here, KL is the factor live load element factor, and area T is the tributary area. The tributary area, for example, if this is an interior column, you go halfway up, sides way half, and sides way half to the next column, then that would be the tributary area. And it is also explained in the examples. So you have here the different definition of these symbols here. Then live load element factor for interior columns is 4. Tributary area in square feet or square meters, so area T. In this reduction formula, the following must be observed. So influence area, which is equal to the live load element factor times the tributary area, should be greater than 400 square feet or 37.2 square meters, so that we can apply this reduction of live loads. Then for members supporting only one floor, the reduced live load should be greater than 0.5 of the design load and reduced design live load per square foot from table 1-4. Then for members supporting more than one floor, it should be greater or equal to 0.4 of LO. Now for the case where B is not satisfied, then use 0.5 of LO. If the reduced live load is less than 0.5 of LO for members supporting one floor, then use 0.5 of LO. For this situation, for members supporting more than one floor, if L is less than 0.4 of LO, then you have to adopt 0.4 of LO. That's the meaning of that. Then D, no load reduction is allowed for live loads exceeding 100 square pounds per square foot or 4.79 kilopascals. Or for structures used for public assembly, garages, or roofs, they are not to be reduced. So this is the formula for SI units. Then square root of KLL area T, because it is also equal to square root of AI influence area. So we define influence area on the next slide. Influence area defined on the next slide. So here we have the table for live load element factor. You can use this for the different members. Interior columns, for example, 4. Exterior columns without cantilever slab 4, and so on and so forth. So you just go over with this. And we have here the influence area. We have here the edge supporting member. We have here the interior supporting member, and we have here the corner supporting member. that's for columns, and this is for beams. Head supporting member, we have interior supporting member and corner supporting member. So typical influence areas, head supporting member, this is the influence area for this member here. This is the influence area for that member. For this member here, this is also the head supporting member, this is the influence area. Interior supporting member, this is the influence area, not the tributary area. The tributary area would be half, so this dimension here, this dimension half to the next column, for example. So that's the tributary area as distinguished from influence area. So that's the tributary area. Then we have here the edge, the corner supporting member, the corresponding interior supporting member for beam, corner supporting member for column, and this one is corner supporting member for beam. This is the influence area. But the tributary area would be this half only to the next beam. For this corner, tributary area would be this half, then half to the left. So that's the tributary area. So example that is presented in Dagler, I uploaded that. Then let's proceed to live loads for bridges. Design live loads. Design live loadings for highway bridges are specified in the Code of the American Association of State Highway and Transportation Official, or ASTO. So that's the acronym, where railroad bridge design follows the specification of the American Railway Engineering Association. So that's for area. Both of these codes give wheel loadings and spacing for different types of trucks or trains. So of course, our trailer trucks and trucks are also based on this. So we will adapt this, although we have our own structural NECP, National Structural Code of the Philippines. So we will have that, but mostly the content of that code were taken from the US specifications. Bridge loads for Philippine setting are under the control of the DPWH and based on the specified bridge loads in the National Building Codes of the Philippines. So we also have National Building Codes. This is the typical truck. This is the total load of the front wheels, center 0.8 of W. This is also 0.8 of W. So the total load would be the 1.6 of the weight of this truck here. So this distance is 14 feet. Then this one ranges from 14 to 30 feet. So this is 8 kips, 0.2 of the total weight is 8 kips, 32 kips, 32 kilopounds. That's the meaning, because this is from the Americans, 32 kips. The meaning of HS truck 20-44, 20 means 20 kips. So if you notice, the first two is equal to the weight of the entire truck. 8 kips plus 32 is 40 kips, and one ton is 2 kips. Therefore, this is 20 tons. So that's why you have here the designation number 20. 20 means 20 tons. And 1 ton is 2 kips, 2 kilopounds. So the first two, front and the center wheel axles, is equal to 40 kips, which is correspondingly equal to 20 tons. This 44 here is the date in 1944 where this truck was standardized. So that's the meaning of that. So W weight of the corresponding H truck total weight on the first two axles, impact. So impact can have greater stresses than when the loads are gradually placed on the structure. So we need to increase the reaction stresses or loads by this impact factor, and this is given. When live loads are applied rapidly to a structure, they cause larger stresses than those that would be produced if the same loads would have been applied gradually. So the impact factor specified by the AS2 specifications is given by this formula, 15.24 over L plus 38.1, and it should be less than equal to zero point 0.3. That's the SI value. Some other books specifies it so that you can easily remember it, 15 over L plus 38. So the decimals are removed. L is the length in meters of the portion of the span loaded to cause the maximum stress in the member. And in under consideration, the English equivalent is 50. So 50 divided by 3.281 will give us that. And 38.1, you just 38.1, 3.281. The original value is 125 in English system. So this is 50 over L plus 125 in English system, and it should be less than equal to 0.3 for this AS2 specification. If the value exceeds 0.3, then use 0.3 as minimum. And this is the English foot-pound-second system. In some cases, provisions for impact allowance are specified in American Society of Civil Engineers 7-10. So just use the NECP, and in problem solving you can have this. Please memorize just 15 over L plus 38. You can easily memorize that. But in most cases in problems, because in most cases and problems that will be given as part of the problem, so you don't need to memorize. But for situations like this, you also have to familiar, because it may be asked in the questions in civil engineer board exams. So weight of elevator machinery to be increased by 100%. So you double that for elevator machinery. Loads on any hanger supporting floors and balconies to be increased by 33%. So you increase the loads by 33% before you analyze these types of structures. Next, wind loads. Wind loads are produced by the flow of wind around the structure. So the kinetic energy of wind considered as 1 cubic meter volume. So it is 1/2 mass velocity, 1/2 mv square kinetic energy, because the volume of wind to be considered is 1 cubic meter, and mass is density times volume. So that's why only the density appears here. This represents the mass supposedly for a unit volume of wind flowing. So it is reduced to this. Now, American Society of Civil Engineers 7 standard modifies the above equation into this complicated equation. This is discussed in NECP also, but all these coefficients, Kz, Kzt, Kd, and we have the importance factor for the type of structure. For example, if it is a hospital or school building, it is important, so it is greater than 1.15. Those are important buildings, and some of these coefficients are close to 1, some are slightly greater, some are lesser than 0.1. So if you multiply all these three coefficients and the impact factor, most probably this approaches to 1 or unity. So I'll develop a formula which will be used in the analysis here, and that formula was also adapted before. So this is the modern formulas, but we can use the simpler formula which I'll derive here, and which shows this 0.613 also. So QZ, the velocity pressure at height Z in pascals. KZ is the velocity pressure exposure coefficients. KZT is the topographic factor. So this one is only important for structures erected in rural areas. KD is the wind directionality factor for wind acting alone, so it is 1.0. I is the importance factor. So this is the table 1-5 velocity pressure exposure coefficient, Kz, depending on the height of the structure. So 0 to 6.85, and it decreases as the height of the structure increases also. So as I said, these factors are sometimes less than 1 and slightly greater than 1. Then I now derive the formulas which we're going to use in our problem solving. So from 1/2 density velocity square, where velocity must be in meters per second. Remember that density from hydraulics and fluid mechanics was pressure over RT. Now, if the pressure is atmospheric standard, then we can assign it as 101.3 kilopascals or 101,300 pascals. So let's make it pascals. R is the gas constant of air, which is 287 Newton meter per kilogram Kelvin, remember? And T is the absolute temperature. Since this formula was developed in the US setting, the temperature is 15 degrees plus 273 to convert that to Kelvin. So remember, 15 degrees Celsius is the standard temperature for engine, as stated by the engineers ahead of us. And for physicists, scientists, 4 degrees Celsius, they have the same value for density. So Q is 1/2 for sure, 101,300, assuming standard atmospheric pressure, then gas constant of air, then temperature 15 degrees Celsius plus 273 to make it Kelvin. So you will get 0.6127, which is this into decimal places velocity square. Finally, because V is in kilometers per hour, let's convert that to meters per second so that this pressure would be in pascals. So 0.6128 times quantity V kilometers per hour square. Then the factor is we divide that by 3.6 square also. Meaning we multiply this further by 1,000 meter per kilometer. Then 1 hour is 3,600 seconds. So 1,000 divided by 3,600 is 1 over 3.6. That's why we have here 1 over 3.6 quantity square. Finally, the formula is 0.0473 V square in pascals. If you want the pressure to be in kilopascals, then divide this by 1,000 further, so that the formula becomes 0.0000473 V square. Let me see. 0.0473 divided by 1,000. So that's it. 4 zeros in kilopascals. So use this if the velocity of wind is given 150, 200 to 50. That's the usual in the Philippines in kilopascals. And I also have examples on that for calculations. So as mentioned, I'll just present to you snow loads, but very briefly you can have it, you can read it by yourselves because there is no snow in the Philippines. So you just go over with this. Just pause the video if you want, but of course I will not consider problems where snow is present. But you might encounter problems in the books where there is snow load, but of course we don't have that. Then earthquake loads. So an earthquake is a sudden undulation of a portion of the Earth's surface. Only the horizontal or lateral of ground motion is considered as part of the building. So if this is the building, then we have here the lateral loads corresponding to that earthquake loads there. According to American Society of Civil Engineers, the seventh standard, the total lateral seismic force that a building is designed to resist is given by this formula here. For base shear, C sub S times the weight of the portion of the structure. So V is total lateral force or base shear. W dead load of the building. C sub S seismic responses coefficient, and so on and so forth. So in our situation, I just give you the base shear generated as an approximate value, but the calculations will be in your earthquake engineering subject later. So you don't need to have a problem on the lateral load because it will be given directly in the problem in structural theory. But in design, you have to compute it, and it will be discussed in your earthquake engineering subject. So as I said, because later on when we have to consider lateral loads, they are given, so you can read this and study this independently. It is only an introduction. The details would be in your earthquake engineering subject. Structural dynamics also. Then we have hydrostatic and soil pressure. So you haven't yet experienced hydraulics, so you just wait until hydraulics and your geotechnical engineering subject for this hydrostatic and soil pressure. So I'll just present it in a short way. Pressure is specific weight of fluid times H depth in fluid mechanics, while in geotechnical engineering, this soil pressure is coefficient K1 and gamma of soil, specific weight of soil times H, which is the same as that, where K1 is a factor that is of maximum value 1. It ranges from 0 to 1, by the way. Thermal and other effects. So in structural theory, this thermal effect will be given, and the thermal expansion of different materials shall also be given. So for steel, for example, 11.7 times 10 to the negative 6, if you can remember the thermal expansion coefficient. Then, of course, they are given, such as fabrication error and support movements. They are given here. So I'll make this fast for this problem because, as I said, you don't need to compute this. They are given. You just compute for the effects by thermal and other effects to the structure. Then for provisions from 2010 in ECP, the current one is 2015. There should be 2019, and this edition will be every 9 years. So supposedly the next NECP edition should be 2019, but there is also 2015 because of the effect of Yolanda. To effect of Yolanda, super typhoon, mega typhoon. So the wind specification portion was edited because of the effects of very strong storm and typhoon. So especially the first one, you have to familiar. But anyway, this is not design and just give you the different formulas as an ultimate load for certain structures. So you just go over with this because you can have this as index card in this subject if you're given with that problem. So you just read, post the video if you want. So I will not discuss more on this because these are subjects in design. Later on. Then I need to discuss this because you need to analyze the floor and how to transmit the loads as one-way or two-way uh, slab. The loads on the supporting beams or a two-way rectangular panel may be assumed as the load within the tributary areas of the panel bounded by the intersection of 45-degree lines from the corners with the median line of the panel parallel to the long side. The bending moments may be determined approximately by using these formulas here. So I give you examples on how to analyze uh, floors, how to transmit, how to compute the loads. So for short span, PS over 3. For long span, PS over 6, 123 minus S over L square, where P is uniform pressure in kilopascals. So you go over with the example and look at the problem. So slab case 1, when short span over longer span is less than equal to 0.5, or if you get the reciprocal, the long span divided by S, short span is greater than 2, then it is considered one-way slab. So supports to consider are on two opposite sides only. Loads are distributed equally on the supporting beams. So remember how to transmit the loads for supporting beams. So uniform rectangular loadings, well, that would be the result for one-way slab. And for instance, this floor here, the load should be transmitted on that side and on this side equally. Case 2, if S over L is greater than 0.5 or L over S is less than 2, it is considered two-way slab and the loading would look like either triangular or trapezoidal. So we have to draw 45-degree lines like this or here, 45 degrees, 45 degrees. So that would be the loading in two directions. So load distribution for a two-way slab, that would be the distribution for two-way slab. Equivalent uniform load carried by the shorter beam, like this. So you have to convert that into rectangular part, and this uniform load is equal to pressure times S. S means the shorter span divided by 3. So that's the W. Equivalent uniform load carried by the longer beam would appear to be trapezoidal, but you can convert this into rectangular as shown. And of course, for situations like it consists of many beams and girders, then we cannot do that. We just use the actual loading system. So S shorter span, L longer span, M is S over L here, this one. You look at the formula earlier, which I directly put S over L here instead of M. Then P is floor load per unit. That's P, that's not density, in kilopascals in SI.